Right. So we look at beams. Now in a tall building, generally beams are very safe elements. The reason is, we can allow certain amount of moment redistribution at the supports in beams. And generally you can go up to about 30% moment redistribution. That means, the support moments can be reduced by about 30%. And sometimes we limit it to about 20%. And when you are when you are allowing redistribution, you have to make sure that the rotation, adequate ductility is available or rotational capacity is available at the columns. And there are few rules to be followed when you are doing moment redistribution. And then you will end up with a higher load, higher moment in the span, because we are reducing the support moment and increasing the span moment. But so when you do the design, you will find that, in the span, the beam can behave as a flange beam. Because it's a flange beam, the flange beams are more efficient than rectangular beams to carry bending moments. So you will find that although the moments are increased in the span, still it can be designed efficiently. And also what we do in tall buildings is we'll provide little extra capacity in the span moments. The reason is when you have a tall building, during the construction, we are adding the load incrementally. So we are not constructing the building at once, we are constructing floor by floor. So when you construct the building floor by floor, what actually happens is the axial loads will not change very much. But in the case of transfer plates and so on, they can be additional moments. But in the case of columns, two adjacent columns can have deformations which are slightly different. Two adjacent columns can have deformations which are slightly different. And because of that reason, you have to expect some variation in the support conditions in the form of settlement. And we know that when there are settlements at a support, the hogging moments will be reduced and span moments will be increased. So to allow for this possibility, when you are designing beams in a tall building, we'll make a small additional allowance in the span section, so that even if the moments are increased due to any support settlement, still the beam will be safe. So that's what we generally do. In addition to that, to enhance earthquake resistance, we generally provide closed links at the columns, so that the beams can easily form plastic hinges and redistribute the loads without undergoing crushing of concrete. So those are the precautions we generally take. And so basically, in the case of tall building, we have to do certain amount of optimization. So the ideal element for optimizing is the slabs. So the reason is, if you have a 40-story building, the same slab will be repeated 40 times. So if you make some saving in the slabs, those savings will be repeated 40 times. So it's good to have an optimized slab. The reason is, if the slabs are properly supported by beams, main beams and secondary beams, then there's very remote chance for such slabs to fail, even if you have optimized. Then you'll ask, what is the reason? The reason is that in addition to the normal behavior, when there are beams at reasonable spacing, the slabs can generate some arching action, and because of that reason, the slabs tend to be fairly strong in resisting the loads. And because of that reason, you will find that slabs will not fail in a tall building. So you can actually optimize the slabs. And one of the ways that you can reduce the reinforcement in the slabs is for distribution mass, you might consider using 8 millimeter uh, high yield bars rather than using 10 millimeter high yield bars. And then when it comes to columns and walls are the most important elements in a tall building because they are carrying the vertical loads. So because of that reason, generally we do not try to optimize the columns and walls too much. We'll make sure the concrete columns will have small amount of extra reinforcement so that we can ensure that the columns will remain safe. And also another important thing that we can do is to ensure that the concrete that we use will contain some amount of fly ash, something like 10 to 15% fly ash. The advantage of having fly ash in concrete is fly ash containing concrete generally tend to gain strength over a longer period of time. So if you include some fly ash, if you want say 30 megapascal strength in 28 days, you'll find even after 28 days, this concrete can gain strength. And finally, it might, after 2-3 years, you might find that the strength has reached 35 or 40 megapascal. So it's useful to have fly ash containing concrete used for columns. And these days, fly ash containing concrete is commonly used. Then the other important thing that you have to consider is the kind of moments. So if you consider a normal design, when you have analysis results, very often you will find that the column moment is given by M.T.R. So the bending moment about 3-3 axis. But in this particular case, here you can see a transfer plate is located at this location. And here you can see the same column. This is M.T.R, this is M.T.R. M.T.R is much larger than M.T.R. So always it's a good practice to check the bending moment about both axes for a column. So when you are designing column, always check the bending moment about both axes. And then this is a building with transfer plate, transfer beams, and we'll have a closer look at these transfer beams. And here you can see the beam is this extruded view. Now beam center line is somewhere here. The walls are located not on the beam center line. Walls are located away from the beam center line. So basically the walls are located on the edge of the column, edge of the building, whereas the beams are located at the center line of the columns. So when you have this type of situation, and you can see that when you look at this diagram also, you can see these are the center lines of the beam, but the walls are located away. Walls are not located on the center line of the column, center line of the beam. Now this is a special situation because generally when we consider beams, we expect the beams to be loaded on the center line so that there's no twisting effect. But in this particular case, the beams are large because they are transfer beams. The transfer beams can be subjected to torsion. So because of that reason, you have to make sure the transfer beams are fairly wide. And we see what is the reason for that. And here you can see, if you have a beam like this and a beam like this, same depth, and here the shear will flow like this. when it's subject to torsion. And when this is subject to torsion, here will flow like this. And here you can see there's a substantial lever arm. Lever arm is large. So this is torsionally strong. This is torsionally weak. So in a transfer beam situation, you have a transfer beam like this. So this can be about 1000 millimeters. This could be about 1200 millimeters. Then you can have a wall here in the center. But the other possibility is you might have a wall here. So what happens? The beam center line is here. The wall load is coming here. So this can be subjected to a substantial torsional moment. So you have to be mindful about this when you are designing transfer plate. So here you can clearly see the walls are not located on the beam, they are located away, and the strategy used is, the strategy used is here you can see. Here you can see some arm has been used to locate the wall at the correct location. And these arms are fairly large sections are used without mass. So you don't actually have this. So you can see the wall is now not supported by the beam, but it is supported by an arm projecting from the beam, so that the exact location of the load transfer from the wall is considered in the model. So in the actual structure, you don't have beams like this, but in the mathematical model, because you want to create the exact situation that you have in the structure, you can make use of rigid arms like this. And so the moment you use rigid arms, what happens is now the beam is not loaded on the center line, it is loaded with an extensity, and this extensity will give rise to torsional moment in the beams. So in the case of transfer beams, sometimes you will find the link used will not be something like 10 millimeter or 8 millimeter. The link used can be something like 16 millimeter or 20 millimeter. So what actually happens is, to resist torsion, you will need a lot of links, and those links could be in the range of something like 16 or 20 millimeter reinforcement. So you get some situation like that in the case of the transfer plate. So as you have seen, some of these walls are located at the correct location, but that correct location means the beams are now loaded with an extensity. So then you can also see on the extruded view where the beams are located, where the walls are located. So the transfer beams may not be loaded on the beam center lines. So they because of that reason, will be subjected to bending, shear, and torsion. So the ideal way is to resist this torsion is to make sure the width of the transfer plates transfer beams are substantial, so that we'll end up with almost a square section, not a rectangular section. Square sections are better in resisting torsion when they are large. So in addition to that, in the case of transfer beams level, at the top we need a slab. So what we do is, for this slab also, we'll not use a small thickness like 125. We'll try to go for a better thickness like 150 or 200, and then ensure that it has 2 mats of reinforcement. And such a slab can actually reduce the rotation in the beams and improve the robustness of the transfer plate, transfer level structure. So in addition to using transfer beams, we'll make sure that we use a proper slab at that level, and the slab thickness may be about 200 or 150 millimeter depending on the spans. But the most important thing is, we'll not provide top and bottom reinforcement separately. We'll provide 2 mats of reinforcement. So we'll have the bottom reinforcement properly designed, top reinforcement also properly designed, but the top reinforcement will be made continuous, so that you get a top mat and a bottom mat, and then you will get a fairly robust and strong slab at the top of the transfer beam level. So then you can have a look at the kind of moments on the transfer beam. So in this particular transfer beam, and here also you can see the torsional moment values can be clearly seen, and all these torsional moments are coming due to the eccentric location of walls with respect to the center line of the transfer beam. So is that clear to you? That transfer beams can be subjected to torsional moments, and how to get the torsional moments acting on the transfer beam from the model. Is that clear to you?
Yes, sir.
Any other person having any questions? So you can see in the mathematics, when you're creating a mathematical model, sometimes we created the mathematical model in such a way that some of these effects will be actually reflected in the mathematical model. So we may have situations where the beams may not be loaded axially, but may be loaded with an eccentricity, which can give rise to additional moments in the form of torsion in the beams. Is that clear?
Yes, sir.
Right. Have you learned how to design a beam for torsion? Have you learned how to design a beam for torsion? Yes or no? Or can't remember? So basically, torsion, I think if you haven't learned, just see a textbook and see how to design. It's not very difficult, but there are few equations to be used. You have learned how to design for shear, is that right? How to design a concrete beam for shear?
Yes, sir.
Yeah, so the methods are fairly similar, but if you look at an example, you can actually find it. If I can find an example, I try to give it to you, right? So you better just make a mark that you don't know how to design a beam for torsion, but designing the beams for torsion is important in case of these buildings, because the beams can be subjected not only to shear and bending, but they could be subjected to torsion as well. Can you understand the principle of torsion? How the torsion comes? Is it clear? Is it clear with how this torsion comes onto the beam? Yes or no? Any answer, please?
Yes, sir.
Oh,
It's clear.
it's clear. Okay. Right. Then now you can see, these are very large elements, say 1000 millimeter by 1200 and so on. So one of the challenges that you get is when you are doing the construction, when you have very large sections, sometimes you have to carefully control the temperature of the concrete. The reason is, if the temperature of the concrete due to heat of hydration exceeds 70 degrees, then you can have a problematic situation called delayed ettringite formation, or DEF. Have you heard about DEF, delayed ettringite formation?
Yes, sir.
Yes. So in large members, then you have to be careful in selecting the concrete grade, and you have to see whether to use grade 30 concrete or grade 40 concrete, right? And so what happens when the strength of the concrete is higher? We have to use more cement. And when you use more cement, what happens? With more cement, you will find that the heat of hydration is higher. So where the heat of hydration is higher, there's a chance of the initial temperatures of concrete exceeding 70 degrees. So because of that reason, when you have large sections, you have to very carefully select the concrete grade. And if you select high concrete grades, then you have to make sure that the concrete grade what we have selected is reached over a period of time, not as fast as possible. The reason is, if the required concrete strength is gained too fast, then you will find that you have to use a lot of cement, and that cement will give rise to high early temperatures that can lead to subsequent cracking due to what we call delayed ettringite formation. And is there anybody who can explain what is DEF? And DEF is, actually ettringite is due to tricalcium aluminate in cement. And what happens is, when the temperature is more than 70 degrees, this DEF, this ettringite will be converted back to its tricalcium aluminate form, and then the reaction again takes place later. But the problem with the tricalcium aluminate is the volume of tricalcium aluminate after the hydration is much higher than the volume before hydration. So what happens is, if this happens later, if the ettringite forms later, that we call delayed ettringite formation, then the concrete can be subjected to high pressures from inside, and that can lead to cracking in the concrete. So here you can see this is what happened in Southern Highway sections mainly due to DEF, and you can see this kind of cracking in concrete if you do not control the temperatures of concrete properly when you are having large sections. So to help people, the engineers, to find the kind of temperatures that can be reached with different cement contents, and also the kind of section thicknesses. Here you can see, the cement contains something like 350 kilograms or per meter cube. That is 1, 2, 3, 4, fourth chart. Here you can see when the section thickness is something like more than 600 millimeters, you may have to be careful. Whereas the placing temperature is 32 and no fly ash or anything. But here you can see the same amount of cement, 350 kilograms with 15% fly ash. So which means it's not all cement, it contains fly ash as well. You can easily go for something like 1000 millimeter thick section without any problem with the ettringite formation. And when you have about 25% fly ash, and you can see a fourth chart containing about 350 kilograms of cement, you can even cast a 2 meter thick section without having any difficulty. And again, the placing temperature is considered at 32 degrees. So if you want to maintain lower temperatures or the lower maximums, what you have to do is take all the precautions so that the placing temperature can be reduced below 32. And how you do that is by using flaky ice as the mixing water. Say about 40% of the mixing water can come from flaky ice. And the other thing that you do is, you will keep the aggregates wet the day before, so that the evaporation of this water from the aggregates will take a lot of heat away from the aggregates. So the aggregates will remain cooler, and because of that reason, you can make sure the initial temperature of the concrete can be maintained at a reasonable level like 28 degrees or 30 degrees. And in doing so, you can reduce this peak temperature also by 2 degrees. So rather than stopping here, you can go up to about some here. So basically, you might be able to cast bigger sections with reasonable cement contents when you are using fly ash. Whereas when you are using only cement, as you have seen in the earlier one, the chances of temperature exceeding 70 degrees is always there, even for reasonably large sections, need not be very large. And here you can see when that cement content is high, which directs us to believe that in our warm tropical climatic conditions, trying to use too high strengths with cement only is dangerous. If you want to go for high strengths, make sure we do it with additives like fly ash. Don't do it only based on cement, because when you have large sections, the first argument is you are needing a very large section because the section is not optimized. If the section is not optimized, don't try to use high strength concrete. Use a reasonable strength concrete like the 25 megapascal or 30 megapascal concrete, which can be easily made by using lesser amount of cement. Whereas if you want higher strengths, then always make sure you go with reasonable amount of fly ash. And sometimes when you do this, you may not be able to achieve your higher strengths in 28 days. Then you might have to set a target like achieving the required target in 56 days rather than 28 days. So you may have to have a little bit of knowledge about concrete technology and manipulate things reasonably to achieve whatever you want in case of larger sections. And these kind of large sections are very often encountered in large buildings. So you have to be a little careful when you are dealing with large sections. And if you are not careful, you might end up with this kind of cracking in an extreme case. And when this type of cracking occurs, the only remedy might be removing that part of the structure and recasting, which will be very costly and difficult operation. So if you look at the transfer plates, now what we have discussed is transfer beams, but in addition to transfer beams, sometimes you might use a transfer plate or transfer flow. And that is, a flow like having a thickness of about 2 meters. And everywhere you get this big, massive structure. And so the advantage of a transfer slab or a transfer flow is it will have a massive torsional capacity. So the only danger will be the punching shear. So you have to carefully check the punching shear capacity of a transfer plate. But the biggest problem of a transfer plate occurring at the 5th floor, 6th floor level is how are you going to support the weight of the transfer plate during construction. So if you have a 2 meter thick concrete, what is the weight of 2 meter thick concrete? 2 meter thick concrete, 2 into 25 will be 50 kilonewtons per meter square. So 2-meter thick concrete can give a load of 50 kilonewtons per meter squared, whereas the floors below would have been designed only for about 5 kilonewtons, 5 or 6 kilonewtons per meter squared, even when you consider the allowance for partitions, finishes, all that. Still the lower floors may be designed only for 5 kilonewtons per meter squared, whereas when you have a thick floor, then it can exert about 50 kilonewtons per meter squared. So how can you support the loads during construction? So to support the loads during construction, you have to do shoring for few floors, so that this load will be distributed over few floors rather than one floor. So which will be fairly costly operation. And another way that is available for you to cast a transfer plate is to cast a slab of about 350 millimeter thick initially, and then remove the props and do repropping, so that once you remove the props, the slab will take its own loads, and after that, on top of this slab, which is designed to carry whatever the load due to transfer plate concrete, we can place this additional concrete on top of the slab that we have already cast. So that's the other way that we can actually cast a very thick slab with minimum impact on the lower floors. So what you have to say is, transfer plates should be carefully considered because they are difficult to cast and expensive to cast. So we have to think of some better solutions as well. And one of the solutions for this particular building is having a transfer plate at this particular level. But we'll see what is the solution that was used in this Cinnamon Red Hotel, that is in Kolpiti. And so basically in this building, there are about 6 floors of car parking, and then there are few common facilities, 7th, 8th, and so on. The actual hotel starts about 10th floor. So at the 10th floor level, there was a transfer plate. Again, the thickness was about 1.5 meters. But in this one, what is done is, this transfer plate is converted to a hollow slab. So basically, it had a 250 millimeter bottom slab, and then wherever the transfer slab is not needed, it was kept hollow, and a set of beams were arranged on top of this bottom slab, and it was cast with the top slab of 250 millimeter thickness. So this way, a transfer plate was created, but it was hollow inside, and concrete was there only where it's necessary. Concrete was there only where it's not necessary. So this way, the weight of the slab was reduced, and also the casting difficulties were removed, and also a lot of concrete and reinforcement had been saved. So there are various solutions, and one of the solutions available is to use the cellular transfer plates, and another solution that is available is to use transfer beams instead of transfer plates. And even if you have a bottom slab and a top slab mixed with the transfer beams, then you will end up with what we call a hollow transfer plate. And on the other hand, if you think it's easier to do concreting and the speed of construction is the key parameter, sometimes you might even consider having a bottom slab and casting a solid transfer plate as well. So there are few different options available for optimizing the structure by using different structural forms for transfer plates. So is that clear? So these transfer plates, you can have transfer beams, transfer plates, or hollow transfer plates. So in this particular building, the transfer plate is located at this level. So up to 6th floor, it's car parking, and after that only you get all this reception and all that. 7th floor onwards, and at the 10th floor level, there's a transfer plate, and then the hollow transfer plate, and then the structure starts. Is that clear?
Yes, sir.
Right. So cellular transfer floors will have a bottom slab, and then you can have some additional supports in the form of shoring from the lower floors, but this slab can be designed to carry whatever the load of beams and the top slab, and the width of the beams can be about 600 millimeters, because we are using a top slab and a bottom slab. The torsional behavior will not be a major problem in case of these transfer plates. The reason is this. So reason is, when you have a beam like this, the shear will flow like this. Whereas when you have a slab and beam like this, so these are voids. These are voids. So when it's subjected to torsion, the torsional shear flow will take place here and here through the top and bottom slabs, and it will go to the end of the beam, and then only it will come back. So here you can see the distance between these two will be about 1200 millimeters. So it's a very large lever arm. So because of that reason, you will find that the cellular slabs are very good in resisting torsion, whereas small beam sections where the torsional shear flows like this distance is very small. Because of that, torsional moment carrying capacity is very low. So that's why we do not like this type of sections carrying high torsion, because torsion T is very low. This type of section carry some torsion because this distance is high, and when you make it even bigger, it's even better. And when you convert it to this form, then it will be very efficient. So these kind of cellular sections are very efficient in carrying torsion, because the torsional shear flow will take place around the top and bottom slabs. So is that clear?
Yes, sir.
So that type of sections are very effective. So what we have discussed today is, kind of fairly overview of different situations that can arise in buildings, so that when you are doing the modeling and creating a mathematical model for structures, you will not do things blindly, but you will have a reason for doing the modeling in a particular way. So that is the reason for looking at all these different options that have been available. Any questions?
Sir,
Yeah.
for the pre-stress type,
Pre-stress?
yes, sir. In the pre-stress type strains using the beam, the most of the weight conveyed to the column, right?
Yeah.
So that means to avoid buckling effect, do we need to consider a large column size for the tall building? Am
Yes.
I right? Sir, is it a benefit, or because
No, actually what happens is, due to the axial load effects,
yes,
the column sizes will be anyway larger.
yes,
And generally the general rule is, if the structure is braced,
yes,
if the clear height of the column divided by the dimension the least dimension of the column is less than 15, then it will behave more or less like a short column. It will behave more or less like a short column, right? So the short columns will not buckle. So the chances are in a tall building, because the column sizes can be 600 by 600 or 800 by 800, the floor to floor height is only about the clear height is only about 3.2 meters. 3.2 divided by 0.8 is only about 4. So there's absolutely no chance for a column in a tall building having a size of 0.8 by 0.8 meters to buckle. Oh, sorry. I think I was muted. Sorry. Shall I answer the question?
Yeah, okay, sir.
So actually what happens is in a column, in a tall building, the column sizes are maybe something like 0.6 by 0.6 meters or 0.8 meters by 0.8 meters, right? So
Yes.
the floor to floor height, the clear height will be only about 3.2 meters. So if you take this ratio, you might end up with something like 3.5 to 4. So a column to become a slender column, one of the general rules is clear height divided by the minimum dimension should be greater than 15. Should be greater than 15 in case of a braced building, right? If the structure is having shear walls and so on, the columns do not buckle easily. So in a tall building, there's very remote chance for a column to buckle. Okay.
Yes, thank you, sir.
Is,
Yes, sir, clear.
yeah,
Thank
sorry.
you, sir.
Yeah, sorry. I was, I was due to some reason muted earlier. I answered the question twice, but first time you wouldn't have heard because I was muted. Right. Any other question like that?
Sir, another question in the idealizing the both frame and shear wall.
Yeah.
Here we are idealizing the shear wall only for lateral loads. So last time you said that to avoid the stress development, we have to consider the shear wall for both axial and lateral loads. So
No. This is how it happens, right?
Yes.
Generally, when you are considering a wall, we'll do a detailing at the wall in such a way that the out of plane moments will not be transferred onto the wall, right? So there are two types of moments that can act on a wall. One is in plane, the other one is out of plane. In plane moments come due to the lateral loads, right? So then what we do is we have to combine the axial load and the in plane load, right? Then we can get the stress distribution, and this stress distribution should not give rise to any tension, right? This stress distribution should not give rise to any tension, and that's what I explained here. Here you can see, here you get the axial load, here you get the axial load.
Yes, sir.
Right? Get the axial load. Here you get the axial load. Here you get the bending moment. This bending moment is in plane, right?
Okay.
Then due to that, you will get a stress distribution like this, or the actual stress distribution will be like this. So final stress distribution will be like this. Then what I said was, you know this force, and generally when you are designing, always make sure we allow for some additional extensity. So for this, now here what you get is axial load. For this axial load, we can consider the corresponding extensity, the corresponding moment due to a 20 millimeter extensity. So out of plane also you can get a small moment and the axial load and design the reinforcement for that particular axial load and bending moment. Is it clear?
Yes, sir. Yeah.
Right?
Now it's clear.
So this is the actual stress distribution that occur. And if you don't get tension here, you are safe. If you get tension here, then you have to be careful because it can actually uproot the piles. The piles, the tension will be transferred to the piles and piles will try to come out. Right? So that's why you have to avoid tension here. So to avoid tension, you have to make sure we have sufficient axial load transferred onto the shear wall.
Okay, sir. Okay.
Is that clear?
Yes, sir. Thank you, sir. Now it's clear, sir. Yeah. Thank you, sir.
Okay, then we'll stop the lecture, and I'll upload the recordings and the PowerPoint this presentation as well.